days on.
Yeah. Look at the agenda carefully. Is there a actual break to go walk around? I've never been to that facility.
I've never been there either. All the kids have been.
Is our name? Where's the name?
Again, I have to look at the agenda. They said that like an hour already has a break just to walk and talk.
I was like, you can't go alone.
Yeah. All set?
You did?
Yep. Okay, welcome to Weather Watch today, our last Weather Watch for the month of November. And we'll start off with the visible imagery today, and what we're going to focus on today is the short-term weather for the upper Midwest for the Madison area. Then we're going to turn our attention to a forecast bust, not the one from last weekend, the snowfall that we didn't really get, but one that was, it's not yet a forecast bust because it hasn't happened yet, but we'll just look at a little bit of the commentary people have about weather forecasts weeks ahead and some of the issues with that, particularly in the social media. And then kind of look at the extended range forecast, look at the travel weather around Thanksgiving. So on the visible satellite image this morning, or early this afternoon, we see basically over the central and eastern part of the United States, generally clear skies. A band of cloudiness that's out off the east coast of the United States associated with a cold front, and we'll see that very nicely and do some very quick diagnoses of the Q vectors and frontogenesis that's associated with this particular front offshore. It shows up really nicely in some calculations, diagnostic calculations that we're doing. Also, this area of cloudiness that's spreading in from the western part of the to the western part of our state, now it's going to overspread all of Wisconsin later today. This is also an area of ascent that we'll see, but because it's relatively dry, there's no precipitation associated with it, but it is causing some cloudiness. We'll kind of diagnose what are the likely primary forcing mechanisms for that. One of the neat things you can see on the image today, you'll notice if you look very carefully at the low-level clouds, these cumulus clouds that are forming in the cold air behind the cold front, you'll note them moving to the southeast, to the northwest flow, whereas the flow at upper levels is diagnosed by looking at the evolution of these high clouds, is moving off to the northeast. And so that's a southwesterly flow. So we have the winds backing with increasing height, assuming that they're geostrophic, that's associated with cold advection. So that's a nice quick diagnosis of temperature advection just using the satellite imagery, and we'll verify that looking at some actual observations in a moment. A few clouds in the lee of the lakes as the cold, relatively cold, dry air moves out over the lakes, creating some light precipitation. We'll see that in we'll see creating cloudiness. We'll see the precipitation when we look at the radar shortly. And again, it's just sort of severe clear all the way down to the southwestern part of the United States. In our weather discussion yesterday, it was noted that some places in southeastern, New Mexico that had dew points down to 1 degree Fahrenheit. So pretty dry air, super dry air down there. And I wonder if that's the risk that increases the risk for perhaps fires in some places down there. You can also see the Mississippi River Valley here, and the extent of it, the soil types are a little bit different here with its clear skies, and as the sun angle gets as high as it's going to get, you can sort of see the range of where the Mississippi has flowed over time. Shows up nicely. But again, a pretty quiet pattern across the United States. We'll go to the next tab, please, to the right. This is our radar summary for the whole United States. Positive reflectivity image. Again, we can see across New York State some snow showers that have developed. Well, I'm guessing there's snow showers to check the temperature and the actual observations, but there is precipitation across New York State going eastward. A few showers down in Florida near the tail end of that front that have moved off the east coast. And then even just into Maritime Canada, you can see some showers of light precipitation moving to the north along the edge of that cold front. We noted the clouds that were over the upper Midwest earlier, and you can see that those are really not producing anything in the way of precipitation at this point, given the dry conditions there. And then there is some light rainfall, light precipitation out in the northwest and the northwestern part of the United States today. And we'll see how that evolves over time as well in the forecast. Let's now look at a surface map, and we'll first start over New England. That's the next tab, please. current large format map. We'll go to the northeast first, over New York State. Check out our lineages there of precipitation. And in fact, it is warm enough for those showers that we saw to be falling both as rain. Kind of interesting here. Rain, I don't know if this is Syracuse. Eric, you know that station? 37 over 34 with light rain. And Rochester is getting light snow, 41 over 28. So even though it's warmer here, they're actually getting snow at this location, rain over at Syracuse. But you can see along the east coast, northwesterly winds, and that's affecting that cold dry air off the coast. Bermuda, I guess, hasn't yet gotten the front, 73 over 63. But yeah, these are pretty dry, very low dew points here, and the dew point depression is relatively large. Nice dry air mass over the eastern United States. Let's go closer to home. And we see it here in Madison, last hour 32 over 17 with a southerly wind. I guess generally overcast skies at this point, and they're high clouds. And you can see to the west of us strong southerly winds. And this will play a role in the forecast for Madison overnight tonight, in which we might see the temperatures level or in fact increasing throughout the night as opposed to dropping off as we might typically expect that to be for temperatures. So broad southerly flow in the central part of the United States. If we go a little bit further to the south, the southern plains.
Anybody see the lunar eclipse last night? There was like an almost total lunar eclipse. It started at like 1:20 in the morning, and I think it was peak at like 4-ish in the morning. I went to bed around 2 and I stuck my head out and I could see a little cookie bite out of it, which was pretty cool.
And so dew points have recovered from 1 degree Fahrenheit to now 14 degrees Fahrenheit in southeastern New Mexico. But again, a very pleasant day over southern Texas. Even though it's cool or chilly for them, I think they probably like the relief from the warm and humid conditions they get most of the year. So, pretty nice day out in the southern plains. And we'll go to the Pacific Northwest, but we saw precipitation occurring there, but it's sort of scattered light rain and snow in British Columbia and Alberta, southern Alberta, parts of Idaho and eastern Washington. Getting a little bit of light rain, 32 over 32, a pretty miserable day with weather like that.
They've gotten a ton of rain up there too. There's massive flooding going on in Washington and British Columbia from that last atmospheric river.
Yeah, in fact, there was a picture today that just said Washington, a woman being rescued from a flood in Washington. It wasn't clear if it was Washington State, Washington D.C., where this was occurring. But yeah, there's been significant rain there, and they'll see some more coming up. As we turn our attention just a little bit to northwestern Canada, you can see temperatures here in degrees Fahrenheit below zero. So a very chilly air mass has developed. Here you get down to minus 35 when you get over to eastern Alaska. And we're going to see a piece of that air mass actually arrive over our area late Sunday night into Monday morning with an Arctic front plowing through here. And that could also create some snow squalls and maybe briefly some low visibilities, but most of the precipitation will happen to our north.
Apparently the sun went down at formerly Barrow, Alaska yesterday, and it won't come up again until January 22nd. They had 15 minutes of daylight yesterday.
It's really kind of fun to put into your phone that location and look at the sunrise and sunset. When they have the next sunrise.
Already till the sun comes up, right? Like 2 months. I don't know. I don't think I could live there. That darkness would just drive me nuts.
Okay. So let's now go to the charts at 250 millibars. We'll start. Here is our depiction at 250 hectopascal with from 12D the sounding data as well as the GFS analysis at this level posted. And we can see sort of a nice merger of 2 jet features across just off the southeast coast of the United States. This presumably is our subtropical jet, and this is a polar-like jet. We'll note here with this polar jet, the strongest winds are downstream of the trough axis. You can see a nice jet maxima extending along the east coast. Shows it really nicely there. So we have a merger here. We see this subtropical jet again a little bit further to the south. There are 2 jets at any given longitude at this point. And I would suspect this is a polar jet, this is a subtropical jet, just due to the location of these. The subtropical jet's typically the boundary of the the air moving northward from convection over the tropics and subtropics. It's that northern edge of it as it gets torqued to the right by the Coriolis force in the northern hemisphere. And it has a baroclinicity, a temperature contrast that's confined largely into the upper troposphere. Polar jets typically are defined as being associated, and both of these jets are going to be associated with a potential vorticity gradient across them. But the polar jets are a little bit lower in altitude, and they have a temperature structure that can often be associated with the polar front all the way down to the surface. So the baroclinicity with these is much deeper than with what you would see with a subtropical jet. But when they merge, that baroclinicity can get grouped together and be seen all the way down from the lower stratosphere all the way down to the surface of time. Okay, let's go a little bit lower. But before you do that, sorry. Another feature to note, we noted the cold air that was over eastern Alaska and the Northwestern Territories of Canada. You can also see a fairly evident trough that's located here at 250 hectopascal. And I would sort of argue we'll see in the forecast a feature that emerges from this region is going to be dropping southeastward over the next 48 to 60 hours. And it's going to bring that next blast of really chilly air to our area with again, the possibility of some snow showers and snowstorms. And that feature it's just made it through the radiosonde network in the northwestern part of North America, and so that should be well sampled by radiosonde and other data. We'll go down to 500 feet. At 500 hectopascal, you can also see the really chilly temperatures in the center of this upper low, minus 45 degrees, minus 46 degrees Celsius at that location. But for most of the country, we see a nice westerly flow, and associated with that in the lower troposphere, we'd expect to see some downsloping and the creation of a thermal ridge in this region, hydrostatically, just because of the warmth. We'll see a pressure trough or trough in the geopotential that's going to set up with this nice westerly flow. But this portends for our area to be experiencing warmer weather over the weekend, so the next couple days warming up, and we'll see that going to be the case. Out over the east coast of the United States, we see that upper trough center just over New York State and Pennsylvania, and it's been advancing eastward over the last couple of days. Okay, again, if there are comments, questions, something you'd like to see, please speak up.
I want to make a comment.
Yeah.
Can you go back to the previous picture you had?
Sure.
300 millimeter?
Or 250 or, yeah.
Yeah. I think it's interesting that streak of high winds out in the Pacific.
This one?
Or the one right there, yeah.
Sorry.
From the middle of the picture up, that gray, yeah, that thing. It's interesting, it's not a jet stream, as we normally say, but it's a region of coherent, stronger winds with the axis perpendicular to the contours. So normally we think of a jet as, being parallel to the contours.
Like this feature here, or
Yeah.
this here, that's,
So this is kind of a coherent structure that's not. It must be some kind of a frontal feature below. I don't know what would cause that. It's interesting to think about it.
I think it probably is a frontal feature. We're probably sampling this jet, not sampling it because there are no obs here, but the way that the analysis is constructed, this jet, it's probably above it's probably stronger at lower levels. And we're just seeing the top of it. It's going to be less, because of the temperature structure, it's going to be less alive.
Yeah, but I mean, one of the things about it is that I think it's important when you look at jet streams to understand that they're not little people running around in a map.
Right.
They're features that are built up by thermal wind and frontal structures at other levels.
Mm-hmm.
And it appears as a wind on one level, but it doesn't move around like a little person on a weather map. It's a structure, a deep structure that's built up from below.
Right.
And I think this brings that home, that you can see a maximum in winds, a coherent structure like that, that's not related to the direction of the winds at all. Okay.
Yeah, so let's actually go to 200 millibars and see if it's stronger there or more evident. You can see there it's following, I mean, this, whatever you might call this feature right here is a little bit more aligned along that. There is this other jet maxima that's not really connected to this, or the one that's
But I think what the more important thing here is that isotherm.
just right here.
the dash line, is that the isotope?
Yeah, these are isotopes.
Yeah, and that's probably suggesting a frontal structure. If there was at a higher resolution or a higher contour interval, you would see probably more of a band of.
Okay. Right, so let's actually we'll go up one again to 150 if we have 150. And it's not really showing up there much. You can see a cold trough here, but that's not much. I think
Well, I think that's related.
yeah. And let's go down to 300. Not really there, so it's somewhere in that's a very weak
Number
feature
yeah.
that's located in that region.
There's definitely a thermal trough though.
Right, that thermal trough definitely shows up here.
And it's along the trough axis.
Yeah.
Yeah.
Yeah. That's kind of neat. Good point, British. Let's go, we saw 300, 500, let's go down to 850, please. And here we can begin to see some of the structure associated with this. The frontal on the east coast at 12Z today. Right, at 850 hectopascal, we can see that there is certainly very clearly a wind shift, almost 90-degree wind shift when you go from Portland, Maine to get that stable. This is Maritime Canada. Really strong wind shift, and you can see a very strong temperature gradient here. We were talking about 452, 751. This is going to be consistent with the front. We have the cyclonic shear across this front, as well as the strong temperature gradient. And we know the next structure is going to slope downward. So it's here at 850, but the surface is going to be a bit further to the east. We're going to anticipate that. As the ice interrupts are going to slope upward over the cold air. And because this is frontogenetical, we're going to expect that there should be precipitation along it to the extent that it's moist enough. Dew-point depressions are relatively small, so we expect this transverse circulation of warm air rising, cold air sinking in the vicinity of this front where it's active, that is where frontogenesis is occurring along it. We expect to see a band of ascent and upward motion roughly in this region at 850. Other thing to note is over the central part of the United States, to our west, we can see evidence of that geopotential trunk, and it's not truly evident here. I wouldn't say that there is a little bit of a thermal ridge that's been created with this warm air coming off the Rocky Mountains. We have the westerly flow along. And so with this trough here and the warm air that's been created, this thermal ridge, you can see a strong area of warm advection. That's localized. And so localized warm advection is one of the terms in the quasi-geostrophic omega equation that would be associated with ascent. We can go back to 500 for just a moment to verify one thing. Is there any obvious trough? There's a really weak shortwave trough over North Dakota, South Dakota, but it's not, I mean, it'd be hard pressed to call this a really impressive feature here. There's a bit of a wind shift, cyclonic wind shift here, but this isn't really perhaps the most impressive upper trough that you would see. So you might anticipate that we're going to see upwards the ascent here diagnosed by those two terms in the QG omega equation, with the warm advection term being the largest. But what we also do is use the Q vector form of that and diagnose the vertical motion by the convergence of these Q vectors. So what I'd like to do next tab, please. Let's go to 925 just to verify again that we have, you just look at that front, see the structure of it. And again, you can see the thermal gradient is a little bit further to the east. See a nice trough. This is in the analysis, not in from the observations. The observations are here, but the analysis is based on those observations in part, as well as the short-term forecast. And you can see a nice confluent frontogenesis occurring along this boundary right here. And again, obvious strong warm advection here. So let's now look at that next tab, which I think it should be Jupiter window. Actually, let's go, yeah, do that first, Jupiter, and then go to the bottom. So in 751, we're working on developing code all the way to the bottom to calculate quasi-geostrophic Q vectors, and then we're eventually going to invert those to get omega. And so here's the 6-hour forecast. This is for 18Z, that front moved a little bit further to the east. These are the quasi-geostrophic Q vectors. I don't have theta on top of here, but also their convergence and divergence plotted here. And you can see a nice band of where we'd anticipate the convergence of Q vectors at this level should be associated with ascent, descent where we see the divergence of it. And to our west, we also see a convergence of Q vectors in that warm air, that region of strong warm advection, which again is another diagnostic of it. What we're going to do next with this, and we'll show this after, Thanksgiving, the next weather watch, we'll be looking at the omega that we get when we actually do this calculation, invert delta, this is the right-hand side of the omega equation. We're gonna go to all levels, and then we're gonna use the successive over-relaxation technique to invert that to get the vertical motion omega associated with the QG forcing. And we can compare it. This is based on GFS analysis. We go back one click on the tabs to vertical motion approximately at this level. And there's that strip of vertical motion that shows up nicely here. It was most evident in terms of the convergence that we saw. Again, we looked at one level and looked at the convergence. It's over a much deeper level. When you invert it, it smooths things out to get the omega. You see some substance behind this front, a band and an ascent here, as well as that region where we saw the QG omega forcing the divergence of Q being convergent. Here you see a much weaker region of vertical motion. That was associated with those clouds that we saw in the satellite imagery. Again, it's not super moist, so you're not going to expect much in the way at all of precipitation, but you do have the ascent in this region. So those things work nicely.
But in terms of a physical explanation, it just doesn't involve a lot of, dynamic quantities like that. I mean, really what you're talking about here is isentropic upslope along the surface. So what you're getting is a cool air mass pushing with kind of a front.
It's moving relative, so you have air
It's moving relative to the air.
Right.
And the air is being pushed up over the top of it
Right.
because it's warmer.
Right.
And so that's really what that's all about. And this Q vector stuff is just a fancy way of showing that.
Of diagnosing it, right. So we just briefly pointed out the Eliason 62 paper, which at the end of it, I mean, you can talk about the story of Eliason circulation, which describes this cross-frontal circulation, but he also shows a nice image at the end of that paper of the relative flow of two different air masses. You can see the warm air rising up over the approaching cold front, so you can get another better sense of this.
It's kind of like a snow plow moving across the road, and the snow's coming up over the plow.
Great.
That's really what you're looking at.
That's right. That is a diagnostic quantity. It's a pretty useful one to get some of that, to understand that forcing, and also to understand the relationship between the quasi-geostrophic advections of temperature momentum and the resulting secondary circulation that arises as well. There's a nice piece in that. So just want to show one example of a diagnostic we've been looking at, thinking about in 452, 751. Let's go to the next tab, please, Pete, which is going to be the short-term forecast. It's not the short-term forecast. Actually, scroll up a little bit. Maybe we got these out of order. Where did I put it? Click on this for a second, please. Yeah, let's go back on this. Go to the meteorogram. Just do it out of habit. Again, relatively dry weekend, maybe some precip Saturday night, Sunday morning. But the key thing here is the increase in temperatures of today relative, tomorrow relative to today, and also today relative to yesterday. And then things begin to cool down on Sunday. Doesn't show up dramatically here, but you see the temperatures by noon tomorrow already begin their descent compared to both today and tomorrow. Temperatures still increasing beyond noon. So tomorrow looks like it's going to be a nice day. And then the sort of the bottom falls up during the day on Sunday. Let's look at the time height section to get a better sense of this. Remember, time runs from left to right on this. And here's this area of Q vector convergence that we saw, the strong localized warm advection, and the response to that in the atmosphere is to have ascent occurring to cool the column. That's the ageotropic response. With that air rising, we get the relative humidities begin to go up. We hear our high clouds getting sort of mid-level clouds during the day, tonight and into tomorrow. But it's not super moist, so we're not expecting much in the way of precipitation. You'll notice at the surface, these strong southerly winds, that's going to keep things mixing out overnight. So even though we're cooling off, we'll try to cool off a lot. We do have strong warm advection occurring, so that's going to keep the temperatures at least steady, if not increasing overnight. During the day tomorrow, these are high relative humidities. They'll probably have overcast skies, but we'll still be relatively mild. And then the really neat thing that happens near the end of this period is we can see the dynamical tropopause, so the 1.5 to 2 PBU surface, just drops all the way down to at least 700 millibars, probably lower than that. And accompanied with that, you'll see that we're going to get stronger. The winds go from southerly to westerly to northwesterly and begin to get really strong and gusty. Just a brief period of strong upward motion as a secondary cold front begins to move through the area. In fact, tomorrow afternoon, we're going to see perhaps a weak front go through. Right, the winds go from westerly to, or from southwesterly to more to westerly. But the real cold air comes in on the day on Sunday afternoon. And with that, there's a bit of a jump in relative humidity near the surface, big upward vertical motion plume as the tropopause begins to descend over us. And it's during that time period, if we could imagine going a little bit further, we're going to have this low tropopause over us. That's going to create conditions that are going to be relatively unstable in terms of the vertical motion. And so lower static stabilities over us, and if we have sufficient moisture at the surface and heat things up just enough, we could get some convective overturning and get some rain showers, maybe mixing in or turning to snow showers during the day, Sunday into Sunday evening before the sun sets. So this is going to be a really interesting feature, and we'll see the evolution of that on the maps in just a moment.
I think when you're looking at that tropopause coming down, it's interesting because you're looking at warm air sinking. And that's an indirect circulation. It's consuming energy. Where's that energy coming from?
It has to be coming from,
Yeah.
that's a good question.
No, I mean, the energy is coming from kinetic energy of the jet. Because as the jet moves, it's moving into a region where there is no jet and going around the curve on the bottom of it. And so the jet is slowing down. And there's a geostrophic adjustment to that because the jet is in some kind of approximate geostrophic balance. And when it's forced to slow down, when it's making a curve around a trough, that generates an adjustment process that is an indirect circulation in the exit region. So initially, the jet builds up its strength from potential energy.
Right, so increases up on the northwest.
And that strengthens it, and then on the exit region, flows moving out of the jet. And so it's got an indirect, it has to have an indirect circulation, and this kind of a thing is what happens near the exit region, especially when you have a northerly flow, you get the subsidence in the sinking tropopause.
Right, so we're going to see that, and it shows up really nicely in the next set of maps that we're going to look at. So you can anticipate it, the next piece that I was going to show, although I wasn't going to describe it that way. Let's go back, Pete, to the first. We'll do a. We can step through the surface now. But I'm going to show you a couple things that are interesting. Again, the band of precipitation out to our east. Here's that region of strong warm advection, weak thickness ridge that shows up here with a thermal trough. Again, that westerly flow we saw at 500 millibars. Descending over the Rocky Mountains, you get this hydrostatically response to that is going to be lower heights, lower surface pressures as well, and higher thicknesses. And here's the warm advection to our west. Let's go ahead to tomorrow morning, 24-hour forecast. And by tomorrow, we're in the warm advection regime. The feature to note is really these really frigid thicknesses well to our northwest. Believe it or not, those will be arriving over us by the end of the day on Sunday. But nice, strong southwesterly flow warm advection occurring over us. Let's go ahead to tomorrow evening, so 36 hours, please. By tomorrow evening, we're going to get a subtle wind shift. Remember we saw those winds were southwesterly, they became a little bit more westerly by tomorrow night. That's kind of a weak first frontal passage, and associated with that, the northeastern part of the state, there could be some rain or snow showers for northeast. But to see the rapid advance of these really cold, low thicknesses to the northwest, and that's going to be coming through on the day on Sunday. So let's watch that. We'll go ahead another 12 hours to Sunday morning. And here's that secondary cold front. You can see the surface pressure trough right here, strong cold advection, thickness advection right associated with that. And the weak low that develops over western Ontario at this point. And really strong cold advection at the base of this trough. If we had a 500 millibar trough roughly in the same location, that strong cold advection in that region beneath the trough would be associated with height falls in the trough, so that would deepen it. So we'll see if that actually is the result of that. And we'll go to 60 hours finally. Has that really strong, really breezy conditions by Sunday evening, just frigid, it's, the bottom's gonna drop out temperature-wise with really strong northwesterly winds. Again, this model doesn't have the greatest vertical or horizontal resolution, but did actually do well last week with the snow to our north. This is still suggesting maybe widespread snow showers perhaps in southern parts of our state, maybe more steadier snow to the north. So let's take a quick look at 500 millibar evolution, and then we'll look at the potential vorticity evolution. So starting at 6 hours of forecast, closest thing we can see is that little that bit of the trough well over to the well more northwest. We did see, we're kind of hinted at, and this actually shows it better than I anticipated, when we looked at the maps at 500 hectopascal, now saying, we saw the warm advection at 850, do we see any evidence of an upper trough at 500? We could note a slight wind shift over the Dakotas. Well, in fact, there is a small vorticity maxima associated with that. And so, just to back up a little bit, when we were diagnosing from the Q-vector convergence ascent in this region, to the extent that this is close to the geosurface vorticity, we had geosurface vorticity increasing with height. The vorticity values were smaller at lower levels. I can't show that now, but we would have diagnosed vorticity advection increasing with height, with passing warm advection also positive. This would have given us forcing for ascent. And so that showed up nicely in the Q-vector diagnostic without having to do all the pieces that I just stated. Let's go ahead to tomorrow morning at 500. Okay, by tomorrow morning, there's a little warp max that's going to go by us that may play some role in cloudiness, but the bigger, and there's yet another feature that's still to our northwest at 12Z tomorrow morning. But the real big piece, I guess, is not really this one, it's this vorticity maximum over northern British Columbia. Let's go ahead 12 more hours and just look at the evolution of this by tomorrow evening. Things are beginning to move across the U.S. With the passage of this is around the timing that we had for the first weak cold front to go through tomorrow. But that piece that was just on the edge of the map is now rapidly been advected down into Alberta. And just watch the change in the size of the vorticity as well as the curvature of this trough. And the more curvature we see downstream of this is kind of a nice feature. One, you have the flow is difluent. We have this sort of piece of vorticity that's lined along the flow. As it gets more difluent, that allows it to begin to ball up a little bit more on the northern cyclonic shear side of a jet maximum. So this is something that could get a bit more productive in terms of its vorticity advection as it goes from linear, stretched along the flow, or oriented along the flow to something that's a little bit more balled up. And downstream of it, significant advections beginning to develop. Let's go ahead another 12 hours to 48 hours Sunday morning. That area of red has increased, as well as the curvature around it. So this is a really potent upper trough. At this time, we can go back. Again, just remember the trough axis is right along Minnesota and the Dakota borders. Let's go back to the thickness advection we saw at that same time, at 48 hours. And it's precisely in the region where we have strong cold advection in the lower troposphere beneath this upper trough. This is maybe something which is going to help amplify height falls in the upper trough to make it even more potent. Okay, so let's take a look at that and get to 48 to 60 hours at 500 millibars.
And that's because the effect of curvature is to increase the centrifugal force component of the dynamic balance, which creates a greater divergence aloft.
So you're flowing more mass out.
You're taking more mass out of the column, and that makes the pressure fall at the surface more.
As well as in the mid-troposphere, I think, as well. We're getting stronger
Yeah,
curvature.
it's a deep process, but below the axis of the jet.
Right.
Yeah.
And so this is a really nice, well-developed upper trough. The one thing that's lacking for any significant cyclogenesis with this, we did see a weak cyclone develops just roughly in this location around Lake Superior. excellent divergence east of the trough, but you notice that the flow is strongly cyclonically curved, and then it's pretty much straight. Small hint of a ridge downstream of it, but I mean, you do see a changing curvature from strongly curved to straight, but there's no really prominent ridge east of it, which would really give this a bigger kick in terms of its potency.
But we have to remember the flow is actually diving out of that map.
Right. Yeah, it's not along, you mean, it's not
It's not
along that
going along that
surface.
map, it's going under the map.
Mhm. So let's look at the evolution of this. We'll do the loop of the lowest PV level that we have, the isotropic level 3, 10 PV surface. Let's just do an animation. So watch this feature come down. Good. Nicely conserved. Unfortunately, this is a little bit fast in the loop, but you can again see this nice trough that sharpens up as it digs southeastward. Don't see much in the way of features you can't explicitly describe by advection, or not by advection, so that this is largely an adiabatic process as this trough again descends in the northwesterly flow and intensifies overburst in terms of becoming more anomalously cyclonic PV overburst. So what I wanted to do next, to stop this, is go to Tropical Tidbits page at the same time. Yeah. No, not that one yet. And this is 54 hours. This is pretty decent. And what we'll do is with a control and the point of the cursor, we'll click on this. We'll draw a cross section from about here. Sorry, somewhere in Saskatchewan, and we'll just come normal through right there. That's good. And then we're going to change that to PV. We'll submit. And you can see we're getting the tropopause. I mean, again, location A in this is really close to is near the center of this, the depth of this trough. There's A, so we have a tropopause that's already down at this time to about almost 600 hectopascals. Really deep intrusion of very high potential vorticity air. The green contours here are ice or potential temperature, so you can see those isotopes bowing up under this huge, massive PV anomaly. And again, a really nice steep tropopause as well in advance of this. Well in advance of this, you can see how the cross-section was aligned. The precipitation that we see in the forecast here is well east of that's that first front that goes by, and this is the second front that's about to come through as it approaches our area. We're located, we're roughly in this location right here, so the cold air is already, at this time, it's already begun to come in over us. But again, you see that nice surface front that slopes upward under the cold air, maybe even a very small fold, really small fold that's located attached to the udder, if you will, of this PV maxima that's in the lower troposphere. Notice also the weaker stratification, the spacing between these theta contours, these isotopes, relative to some sort of background stratification. It's much more weakly stratified here, which means the possibility of convection occurring. It would be shallow convection, it's not going to be super deep. It's going to be really cold aloft. If we can warm up the surface any with any sun, that might produce some convective showers. I don't know, Greg, if you have any comments to make about that, the possibility of squally weather or showers.
Yeah, there's an interplay here between the frontogenesis process, which is packing the contours along an angle to create packing the isotopes along an angle, and then the fact that they're being spread out because of dynamically induced subsidence on the warm side of the trough.
Right.
And so that's called dynamic destabilization, and it has to do with the accelerating downward flow on the warm side. And that's the indirect circulation. So the indirect circulation happens to set up weaker stability, weaker static stability. And if there is moisture in the boundary layer brought in, because of the dynamic destabilization, you tend to get spreading isotopes aloft, which lower the static stability. But at the same time, the circulation is pulling up the warm conveyor belt below. And that warm conveyor belt is fraught with moisture. So as you pull the moisture underneath and destabilize the middle troposphere above, the combination can create additional instability. And that then would give rise to thunderstorms that might form in that section. So even though...
Are you thinking more about out here, well ahead of this, or really closer into underneath the
Well,
other?
when you get closer in, you're destabilizing it a little bit on the warm side, but on the other hand, you have forced lifting because you get into that region where there's divergence aloft.
Right.
And that's lifting the air there.
Let's actually look at omega. There's an option for omega in this cross section. Relative humidity and omega maybe. No, not that one, sorry. And so here is this huge plume of vertical motion high relative humidity. Now, obviously here where it's really cold, you could have very low moisture content, but because the saturation mixture ratio is lower and the temperature is lower, you can get high relative humidity. But you can also see those strong vertical motions in this region right ahead of the upper trough. So this might be the showers and the dynamical lift ahead of the trough as it's approaching. By this time, it's already past us, so this is near the middle of the cross section, which is southeast of us. Probably getting to the region where there's actually
I think that's in the southeast. And once that starts to happen, one of the other consequences of it is you see that low-level inversion that's forming there, because you're pushing isotropes down, and then they tend to pack up near the ground.
Right.
And that forms an inversion which protects, which inhibits spontaneous convection.
Mm-hmm.
But if you can break through that inversion, you can become you can have very intense convection because of the destabilization aloft. And that's basically what you're forming there is a loaded gun sound.
Way to go. Want to get another dam triggered to really...
If something could break that inversion, you trigger it, it's a loaded gun.
Can you go back to the PB one, is that easy to pull up again?
Go back to TV. Yes, Brad.
So that negative potential vorticity anomaly right in the jet floor is probably from convection.
That could very well be, yeah. I think that's likely the case, yeah. So these negative values are going to show up as really super blue right here. And it's kind of disrupting the structure of this jet. That's not a nice jet core. You actually see it's kind of jagged. Maybe part of that's, as Brad's suggesting, is this.
What's interesting about that is that's way up at 40 degrees latitude. I don't think that's from deep convection at 40 degrees latitude.
Do you think it's air that's coming from the subtropics?
I think it's air coming from the subtropics.
But it's got to be gradients, vertical gradients in Lake Erie.
This is a subtropical jet, and often you'll have pockets of negative potential vorticity on the south side of the subtropical jet. That's what I'm guessing. I don't...
It's getting infected there.
Infected, yeah. It's
Into the
coming-
plane of the cross section. Let's go back in time. Just go back. I mean, it's not going to be the same air mass that's going to the cross section. Yeah, keep that. So 48 hours. Again, this is, and then go forward again. Yeah, this is probably the best way to do it, but, and then one more. Also, notice it's interesting that these multiple jet-like structures that show up. I guess the best way to see this is there anything being ejected in. We close this out for a second, please, and change our map. 330K PD. That may be at the wrong level. Not the best level. And this go back one shot back. 54 hours. That was the time we got.
This is 48.
Right, yeah.
Why don't you go up a little higher, like 340?
Yeah, fortunately, we don't have it here in terms of the options, let's say the higher level. We could look at the two PDUs, pressure and wind. That might give us some clue as to what's happening. 54 hours?
Let's see if that-
Yeah, it's hard to see. I mean, we actually go back a couple steps, time steps. And this air to the south is from the subtropics. Did any of that eject? think what we're looking at where that negative area was southeast of us. So I really don't see it making it all the way up here. So either convection, although it looks like more stably stratified precipitation that precip to the south. But the only way you're going to get these very low values of PV in the upper troposphere or stratosphere is through grades in diabatic heating at some point in the history of that air mass. And whether it was just a few hours ago or several days before it got affected, it's a little trickier to say based on this very short analysis. But the last thing I wanted to do here is, let's go to back to the tabs and go to Twitter. So one of our former graduates of our program, undergraduate, master's, and PhD, Nick Basel, just noted, he's now at Sunyoni, just noted a page that CNN had put up on the 16th, which was looking a week ahead at possible impacts from really severe weather. And they were taking into account the size of, the magnitude of the storm. They were talking about moderate impacts for traffic and travel early next week. And then Tuesday they had sort of major impacts over the Northeast, down East Maine into the Boston area and then parts of northeastern Pennsylvania and West Virginia. And what Nick had said in this was, they were talking about a potentially significant storm hitting the East Coast on Thanksgiving week. CNN's putting this out here. What's really gonna, is this really gonna happen? Is this the right sort of graphics to portray a potentially high impact weather? Now, certainly you want to alert people to the possibility of that, but this might be a little bit over, he was suggesting, at least my read of this, a bit over the top, a little bit premature for this forecast. If you scroll down a little bit just to give full fairness to what he tweeted, it says, definitely the threat of a significant storm, but he was suggesting that perhaps it was far from certain, and he was noting even at this time that the model, this is on Tuesday, if I got my dates right, that the models are less enthusiastic than the ones on Monday, and so he was suggesting the odds that the CNN forecast verifies as being quite low. So let's go to some of the maps that folks at CNN were perhaps looking at on Monday, the next tab. And this is what they were seeing. All right, this was a forecast, 204-hour forecast. I mean, this would be just incredible. I mean, I would love to experience a storm like this. But do you say, again, this is over a week out, maybe almost 10 days out, or 8 days, 8.5 days out from when this was going to verify. You see a cyclone like this, an evolutional cyclone, you can click back and forth over time to kind of get a sense of what's going on. This looks pretty significant, but when people are beginning to plan their travel or have already planned their travel or thinking about it, should I cancel my plans? And CNN puts out a statement that, this is going to be major impacts for travel. That's something you want to factor in, but what really happens here? So I think we can go this way. If we just click through runs so they're all valid at the same time, let's look at how the forecast evolves. Still looks pretty significant. And then look at this. All the development perhaps occurring offshore, but that's just one run after several that were pretty intense. And we keep clicking. There's some wind and some rain. And now we're looking at forecast initialized on the 16th at 12Z. This is just a windy, chilly day with lake effect snow. That could certainly impact travel and some of the East Coast airports because of strong winds. Just maybe backing in. This is on the 17th or so still a lot of rain, but cold. And then the last several runs that have occurred. This tells you on the 17th, 12 on the 18th. You can see snow showers, but if we keep going ahead in time for these runs, one of the things that you'll see is the complexion of the forecast has changed. Again, these are all valid at the same time, Tuesday, but the forecast hour is getting shorter because we're getting closer to the verification. So we're now at today's forecast. And we can do one more click, I guess. Is that right? Yeah. Or is that it? For the next runner. This is initialized 12 to 19. So that's it. So instead of having a double barrel area, two cyclones right off the East Coast, southeastern Massachusetts, and just off the New Jersey coast or Maryland coast, we have just strong cold advection, a few snow showers in the forecast. Eastern Maine, far eastern Maine is getting a little bit of snow. But that's not something, or even a few forecast hours before this, doesn't look to be a big impactful event for travel beginning on Tuesday for Thanksgiving.
So what was the predictability in this, assuming this last one is pretty good?
Right, so yeah, we don't know, so I'm gonna say all of this with, could something change in the forecast? Could something significantly change that ruins it? And in terms of predictability of this, I think there are a couple of issues, and some of them stem from what we experienced last week's forecast for just that short period for the weekend. The trough that's expected to pull over us in the next 48 to 60 hours, the trough we were looking at with a strong cold advection, maybe some snow squalls on Sunday afternoon or evening. That's located in far northwestern Canada over Alaska. It's just coming into it's in the radiosonde network. Certainly we have satellite data, so I'm not going to claim there's no data out there. But at least it's also constrained by some of the surface observation. That same feature, which I think is responsible for the cyclogenesis that's going to occur along the East Coast, about 10 days ago, that wasn't over Alaska or Canada. It was somewhere perhaps over Asia, or over Japan, or maybe over the far western Pacific. And so I wonder, it's just the quality of data. Where was that trough, the initial trigger for this event? And you could probably go back in time and sort of look at the trajectory of it. When was new data? When did it really have lots of observations sampling it? Again, we live in an age where satellites can provide a lot of data if that data is properly used.
But that's assuming it's a data problem.
Yeah, that's assuming data problem. It could be a model problem.
Or it could be that it's just unpredictable because it's too nonlinear at that point.
But the more data, the better you can see.
The more data, the better.
Great.
Do you run a ensemble on one student?
It could be run, and that would have to be a long ensemble. I think the way to do it would probably be, you want a global model, but don't want any boundary conditions with it. But an ensemble of the MTAS might be something. That's good. Yeah, Brad.
There, do you have the spaghetti plot? I mean, they should have the GIF ensemble showing.
We should be able to get that.
There's the ensemble.
GIF.
That is normally, let's
Do they
see.
just show spaghetti plot?
I don't know, it has one somewhere. I don't, it's often difficult to find where it is. Not good. This is forecast trends.
Yeah, I don't think it's.
Yeah, this site doesn't have it, but I mean, NOAA does have, if we just do NOAA spaghetti plot, do a quick search, I have to watch the heads up here, you're getting close. There's a, oh, I should take it, one. So if you do NOAA spaghetti plots. Not to get people hungry, but, not that, ensemble weather maps. Let's look at ensemble weather maps here for physical science and web. Check that one out, perhaps. And it's unfortunate that you're how far out that was. That's 100 and, let's go 120, I think. Is that right?
There's better ones.
That's Wednesday. Go back. Quick, let's go to 96 hours. This is on, we're looking at Tuesday sometime. And so what this shows, an ensemble forecast is run. I can't recall the size of maybe it's up here, the number of members in that ensemble, but it's a collection of forecasts initialized for this all at the same time with slightly different initial conditions. And by looking at the spread in the forecast, here they're looking at two particular height contours, the 552 decameter contour, the 576. The spread in those contours gives you some measure, at least your confidence in the forecast. It may be totally misplaced if all the models are going wrong the same way. But that spread does give you some idea of, gives you some level of certainty or confidence in the forecast. And at least for the forecast initialized from 0Z last night for 96 hours out, the position of this trough along the East Coast, or just off the East Coast, is pretty well, that looks pretty decent. If we look at the mean sea level pressure and thickness, if we can bring that in, hopefully that's on a mean picture. Yeah, there's a cyclone in eastern Canada and cold advection here, but that doesn't look like it's not apparent. I'm not looking at surface variables, so it's a particularly problematic travel day for something like that. But what would really be nice is if we could look at these plots from a week ago, right? And then look at the spread in the forecast at that time period. But we've seen them slowly converging toward a situation where it's going to be chilly on the East Coast, maybe some lake effect snow showers, but most of the precipitation Tuesday into Wednesday is going to be well offshore. And for us, if you go back to Pivotal or something you can bring up quickly, the forecast for Thanksgiving here. The 144. For us is a nice, at least it'll start the day relatively warm, but we're going to already got a cold frontal passage, right? You can see the trough there, the cold advection, geostrophic cold advection coming in. So early morning will be relatively warm, and the day will be, if this verifies, should be a pretty decent day, but temperature's falling in the
What
afternoon.
about that Atlantic storm? Is that gone tropical?
Yeah, so something happens in the Atlantic and then it just rotates around, spins out there.
I mean, it's now, it looks like it's so symmetric, it might be tropical.
Right, and it's warm core, I believe, so that's something to look at for later. Unfortunately, I had to run to take a phone call, but it looks like you have a great Thanksgiving coming up. Again, the weather, nice tomorrow, really nice tomorrow, maybe cloudy, somewhat cloudy, but then it gets kind of gusty winds during the day on Sunday with maybe a few rain or snow showers. Really cold Sunday night into Monday, and then we warm up for part of the week, and then by the time we get to this time next week, we're going to be, by Thanksgiving Day, we're pretty relatively warm, and then we cool off again as we move into the weekend, post-Thanksgiving weekend. Anyway, thanks again for your attention and
No
how
weather
much
watch next week, no weather watch.
Right, no weather watch next week. So, thanks very much.
Unless it's a super event,
Great.
you might do one online, but
Great. We could do that online if there's
If there's something really interesting going on, maybe,
it
yeah.
doesn't look like it now.
I'll look.
Thanks. Yep.
Okay, my class at the normal time.
That's going out.
Tuesday, I think I have,
Yeah.
and we changed